In this video, we will be solving some of the problem based on tau and sigma functions. So let's take, before we solve the problem, let's take the basic definition of the tau n function. Tau n function, it is nothing but it is the number of divisors of n. And n here I am considering a positive integer. And sigma n, this is the sum of the, again, positive divisors of n. Now there are few results that I have listed here in the bullet points, which we can easily see in any of the book based on the elementary number theory. For reference, now I am taking the book here, which is based on the, so for reference you can take the book Elementary Number Theory. And I'm writing DM Burton. So that's the author name. So I've considered my problem from this exercise based on tau n and sigma n function. So the first result says that if there is a two arithmetic function which are associated with this function, then tau n has this representation. All these results are already proved there. And if n is the prime factorization written in this canonical form, which is given as star, then we know what are the formula that we are going to mostly use for sigma n and tau n. And any divisor d of n, where n is given by the star equation, then it is of the same form, where the exponent ai's are always less than or equal to ki's. And then the second last result says that if n raised to power tau n, this is nothing but it is square of the product of the positive divisors of n. And the last result talk about the multiplicative function, that if a function f is multiplicative, then we can write f of m of n is equal to f of m into f of n. Now let's start taking some of the problems. So the first problem here is to solve about this, where m and n are two positive integers given to us, and it has also been given that there are distinct primes and which divide at least one of m or n. Then m and n may be written in the form m equal to this and n equal to this. Now this is very obvious, and then also we want to prove that GCD and LCM is of this type, where ui is minimum and vi is maximum. So let's take one by one these all the cases. So in the first case, what we want to show is we have been given m and n belongs to positive integer. This is what is given to us at the very first stage. And it is also given that these primes p1, p2 up till pr, these divides m or n. So this is all given to us. Now if it divides m or n, this means m can be definitely written in the prime factorization of this form, p1 up till pr kr. Suppose if there is some prime which is not dividing m or r, in that case we can take the power of that particular prime to be 0. So that means that particular prime is not in this prime factorization. And similarly I can take n is equal to p1 to some power j1 up till pr to some power jr, and again with the same logic, this ji may be greater than or equal to 0, and we can say that I varies from 1 to r. Okay, now what we need to prove is, now we need to show it. So the first, these two things are little obvious. Now what we need to prove further is that the GCD of this is given in this expression. This is what we need to prove it. So let's take the right hand side of this expression. So let me to first write what we need to prove. We need to prove GCD of m and n. This is equal to p1 to the power u1 up till so on pr to the power ur. And where, what is ui? Ui is the minimum of ki and ji. And you know, these are the power that we have written here in the expression number 1 and in the expression number 2. So ui is the minimum of these powers. Okay, so this is obvious also, because if we want to take the GCD is greatest common divisor. So it has to be the least which comes in the power. But let's see how to write this and prove this mathematically. So in this case, let's take here now, because now there are two possibilities, because ui is minimum of ki and ji. So there are only two possibilities, as 0 is less than or equal to ui, because the least possibility value is that ui can be 0. It is less than or equal to ki, or we may have that this is less than or equal to ji. Now in this case, where if ki is less than ji. So this means ui can be equal to ki. Suppose here my minimum value is ki. So this means ji is strictly greater than ki, or maybe even you can put equality. It doesn't matter. The equality means all these quantity ki, ji, ui will be equal. In this case, where if ji is smaller than ki, so I am taking two possibilities. Either ki is smaller or the ji is smaller. Now for the first case, this means and I'm also considering this expression as, let me to call this expression GCD as x. So this means whenever this ui is less than ki, and we have this sort of expression, and m has this sort of expression. So we have just done a result. We see here every divisor must be of this form. So if it is of this form, it becomes a divisor. So in the same way here, this means that dx divides m, because we have considered this quantity as x, and this implies x divides n in the similar manner. Okay, so now from the first case, if I now further want to look up, now if it happens 0 less than ui less than or equal to ki, because ki is smaller than ji, so I now further, this means x must further divide n also. And this expression further gives me 0 less than ui less than ji, and if ji was a minimum in this case, there were two possibilities, either ki is minimum or ji is minimum. So accordingly we are running now these cases. So ki is less than, this means x divides m. So in all, so x divides m and x divide n. So in both the possibility this holds. Now for greatest common divisor, the first condition is that x must divide m and x must divide. And if there is any other divisor, then that divisor should also divide this quantity. So let's prove that case also. And here I'm just writing for these value, I can just smallly write it as r. Okay. Now we want to prove the second condition of the GCD. So now take D be any other divisor of m and n. And if it is any other divisor, we know how this divisor is. It will take a form p1 to the power a1 up till pr to the power ar. And because it is a divisor of both, so this means these ai must be less than or equal to ki, and these ai must also be less than or equal to ji. Okay, so because we say that D is a divisor of m and n. Now again, if you look at this possibility, there are again possibilities, either ki is equal to ji. This is one of the possibility. In this case, what was ui? Ui was by definition that it is minimum of ki and ji, and we are saying that both of them are same. So this itself means that ui is equal to ki is equal to ji. So in this case, this d, and so this means, and if we look at this x again, now these ui's, this d must divide this quantity x, because ki, ji and ui are same, and here these ai's are smaller than these ki's and ji's, so d must divide x. So any other divisor that we have selected is dividing now that quantity that we have considered as the GCD. For the other cases, if ki is less than ji, suppose if ki is less than ji, in that case ui, which is minimum of ki and ji, now ki is smaller, so what is the value for minimum of this? That means it is ki. So this means again, if ui is ki, so from here ki ai is still smaller than ki ai. So this means now ai is less than or equal to ki, and ki is ui. Still this follows that this d must divide m. And if d divides m, so this means d must divide further the x, because x divides this quantity. And similarly, if ki is greater than or equal to ji, so similarly we get that d divides this further quantity x again in this case also. So in all situation we get that there is another divisor which divide this quantity, and so we have that the GCD of m and n is equal to x, this whole quantity. So this whole means that we have proved our first case, which shows that GCD of this quantity is equal to this, where ui is equal to minimum of this case. Now let us show the next case, which is based on the LCM. So let's take in this case. Now here I have already written the proof for that LCM, and let's see how does we prove. We want to prove this LCM where Vi is the maximum of this. Now again, if Vi is maximum, so there are three possibility: either Ki or Ji are equal, or Ki is greater than Ji, or Ki is smaller than Ji. For the first case, this means Vi's are all equal. For this case, Vi is equal to K, and if Ji is bigger, this means Vi is equal to Ji. Now for these three cases, we will be discussing them separately. So we have, as Vi is maximum of this implies either this case or this case. So I have written, this means Vi is equal to Ki or Vi is equal to Ji. So this means Pi to each Ji's divides. Now why I have written here Ji's? Because Ji's are greater than this case. So Ji is now smaller quantity. The smaller quantity must divide the bigger quantity. And similarly here, Ki's are smaller and Vi's are bigger. So Pi raised to power Ki must divide Pi raised to power Vi. Now if this holds for every I, here this expression holds for every I. So when it holds for every I, it holds for its multiples. So we get n divides y, and here we get m divides y. So this means y is a multiple of both. So this holds star. Now if we can show that there is any other multiple, that proves the definition for LCM. Now suppose that we take any other multiple z. So m divides z and n divides z. If m divides z, that means every pi raised to power ki divides z. And for n, we have considered pi to the power ji divides z. Now in this means, if ki is equal to ji, then this is the same expression as we have discussed, and this expression implies y divides z. If ki is strictly greater than zi, then we got again y divides z. If ji is strictly greater than z, we get y divides z. So the LCM definition is followed. One, it is a multiple of all this, and if there are any other multiple, then also it follows the definition. So LCM of mn is equal to y, and the result holds. Now in the second problem, what we want to prove in the second problem is, we want to calculate the GCD of this and LCM of this. Now here I am going to use the problem number 1, and let me to call this as m, and let me to call this as n. You see here, this is both quantities are exactly same. So m is nothing but 1, 2, 3, 7, 8, and here n is nothing but it is 3, 0, 5, 4. Now in the previous case, what we have just seen, we have considered the GCD of these two quantity, and we have also considered the LCM of these two quantity. For GCD and for LCM, we wanted to write the quantities into the prime factorization. So let's write the prime factorization of the first case. So let me to write first here. It is 2 into 3 into 2063. I'm sure you can verify the prime factorization. And 2 into 3 into 509. So this is the prime factorization. So it is very clear from above. 2 into 3, that is 6. That's the GCD. And from above we get that this quantity is the least common multiple. So we can directly apply the previous question to get the answer of this question, and otherwise there are separate ways you can apply Euclidean's algorithm to find GCD and LCM of this question. Now in problem 3, again we want to use the problem number 1, and we want to show the standard result that if we multiply GCD and LCM, we get the product of these two quantity for positive integers. So let's write now again. We have considered the product of, let me to first consider the right hand side. So mn is this expression. Now I am using same, m consists of the power k1 up till kr, and n consists of the power j1 up till jr. So when we multiply, power get added, because we remember this was the expression that we have used for m, and this was the expression used for n. So these are the same prime, so the power will get added, k1 plus j1, kr plus jr, and so we get these quantities. Okay. Now what we want to show is, and what was the u? U was, we have an expression in terms of u, ui's and vi, which is minimum and maximum of Ki. So what we remain to show here is if we can show simply this quantity. And why is this? Let's directly come back to this step first. You see here, Mn is nothing but GCD of Mn. What is GCD of Mn? It was written into this form. LCM was written into this form. If you multiply now these two terms, that means the powers are going to add U1 V1. And if you want to prove this side, if you want to prove star will hold when the because the base on the left hand side in equation number double star. Now double star will hold if the powers are exactly equal. So this is what we wanted to show. So if this hold, so the result is true. Now this is very obvious. Looking at this definition of UI VI, this is minimum, this is maximum. Let's take now. There were three possibilities in Kij. Either the Kij's are equal, or Ki is greater than, or Ki is strictly less than. If Ki is equal to Ji, so by definition, if Ki is Ji, then Ui is equal to Kiji, and Vi is maximum, but still both are same, so Vi is same. So Ki plus Ji equal to Ui plus Vi, this holds trivially. If Ki is greater than Ji, now what happened? If Ki is greater than Ji, this means the smallest quantity Ui will become Ji here, because we want to choose minimum in Ui, and in Vi we want to choose the maximum. So maximum is now Ki, which is written here by definition. Now you substitute Ki as Ui and Ji as Vi. Still we get the same expression. And in the similar way, Ki less than Ji, we can get this expression. So it is very obvious, it is very clear that from problem number 1, this result also hold. Even there, we can prove this result by the divisibility test. But here we wanted to use actually the applications of divisibility divisor function, which is arising in the tau cases. Now let's take the next problem, which is problem number 4. Now here problem number 4, it says, in the notation of problem number 1, show that the GCD of Mn is equal to 1 if and only if Ki into Ji is equal to 0. Now just from the previous case, problem number 1, we know that the GCD is given by this equation number 1. And when I say that the GCD of Mn is equal to 1, so the only one possibility here is that each prime should be having the power 0. So when it has the 0 power, that means, so this means if and only if Ui's are equal to 0. If Ui's are equal to 0, so by definition, what was Ui? Ui was minimum of Ki and Ji. This was minimum of these two. And this quantity is 0. This means minimum of Ki and Ji are 0. Okay. So now we don't know which is minimum, either Ki or Ji. So we got this condition, either Ki is a 0 or we got either Ji is 0. So whichever is 0, the product has to be 0. So now let's take the next problem here, and which says problem number 5. So in the 5, we want to verify tau n, which is equal to tau n plus 1. So n plus 2, n plus 3 holds for this quantity and for this quantity. Now I'm going to prove for the first case, for n is equal to 3655. So because we want to calculate tau n function by definition, let me to first write this into the prime factorization. So what does the prime factorization? This will give me 5 into 17 into 43. And if this quantity is the next quantity, because then we want to find out what is n plus 1. So n plus 1 will be 3656. So this quantity would be 2 to the power 3 into 457. So here I am writing the prime factorization, and I'm sure you know how to write the prime factorization. So 3 into 23 into 53, and then we have 3658. That's my next quantity, n plus 3. So this quantity is 2 into 31 into 59. Now we want to write here tau n. Tau n is what is by definition? Whatever is the prime. So we remember the definition. This is k1 plus 1 up till so on up till kr plus 1. This is the power of the primes. So this quantity, this is 5 raised to power 1, 17 raised to power 1 and 43 raised to power 1. So this is 2 into 2 into 2, and that makes it 8. Similarly here, The first prime contains the power 3. So the first quantity is 4 and the second quantity contains 1. So this is k2 plus 1. So this is 8. And similarly we calculate, sorry, this was n plus 1. So n plus 2 is then 8 and then we have tau of n plus 3. This is also 8. So this was what you need to show it. It holds for star. Similarly, we can verify result for 4503. Now suppose that we want to now do the second part, which says when n is 14, 206, 957, we want to show sigma n is equal to this. This is also simple. Say sigma 14 and we want to calculate here. This is sigma n and this is sigma n plus 1. This is 15. Now sigma 14 is nothing, but let's first write this into prime factorization. After the prime factorization, either we can use the formula or we can use the definition. What is the formula of sigma n? This is nothing but p1 to the power k1 plus 1 minus 1 upon p1 minus 1 and so on up till pr to the power kr plus 1 minus 1 upon pr minus 1. So what is the first prime here? This is 2 and the power will become 2 square minus 1 upon 2 minus 1. And this, the second will become 7 raised to power again square minus 1 upon 7 minus 1. This quantity will become 4 minus 1. This is 3 by 1. And the next quantity will become 7 square, that is 49 minus 1. This is 48 by 6. So we can actually cancel it out to some quantity. So this will become 8 and then we have here this quantity as 24. We could have also applied here in this case, we can also apply the case that sigma is multiplicative. Sigma is multiplicative. So if the sigma is a multiplicative function, because the GCD of 2 and 7 is 1, so we could directly write it is same as sigma 2 and sigma 7. So that also give me the result as 24. So we can apply in any of the form. And for the sigma 15, we can multiply it as sigma 3 into sigma 5. And this will give me the result as again 24. So again star holds. And similarly, we can find results for 206 and 977. Now in the next case we want to prove is that tau n is less than or equal to 2 to the power root n. So for this case what we need to show is that for every positive integer n greater than or equal to n, tau n satisfy this inequality. And here we want to use the divisor function. So let's take that. If d divides n, then either d is less than or equal to root n or n by d is less than or equal to root n. So this result holds very quickly, because if we take d as the divisor of n, then d is always less than or equal to n, and similarly n by d is also less than or equal to root n. So I'm going to use this as a result. So you can use this as a hint or maybe a starting result to prove this question, as this inequality always holds. So now what we want to show is, for if both d is greater than root n and n by d is also greater than root n, okay, then d into n by d is equal to n, which is greater than root n into root n, which is equal to n, and that will give me a contradiction. So from here you can validate the previous case result. So this validate this case. So if d is less than equal to n, n by d is also less than equal to s. So if both of them are greater and this is greater, then we arrive to a contradiction. So that means we can take this case as one of the case as the starting result. Now let's take d1, d2 up till so on dk be the divisors of n. be the divisors of n, where d1 is strictly less than d2 is strictly less than dk. Now clearly, because these are the divisors of n, so the first divisor has to be 1 and the last divisor has to be n itself. Okay. Now since whenever di is a divisor of n, so this implies so it's a divisor of n, so this means di divides n, and so n is divided by di. We may use this notation also, because if di divides n, then n by di will give me actually another divisor, which I may say as di dash. Okay. Now pair up these divisors. So you select a divisor and then we take n by d, that will give me another divisor, so d dash. So we want to pair up these divisors. So this implies we have di, and let me to call it as the another divisor, which here I have written as di dash, or maybe I can call this as dj. Okay, so this is equal to n. So where I have considered n by di is equal to dj. Now there are two possibilities in this. Either di is smaller than dj, or dj is smaller than di, or they may be equal. So let's take both the possibilities. Either di is less than or equal to dj, or di is greater than or equal to dj for each I and j. For each I and j. Now we want to take this whole possibility for two cases. Now suppose if we have this pair giving us the equal quantities. So now suppose this pair di dj is such that di dj multiplying, it will give me n, and there are k by 2 unique pairs, and I'm considering here k to be even. So suppose there are even number of such pairs that we have created in this pairs. So in this means, and we also consider that di is strictly less than dj. Okay, and let dk dash be the largest of these di's. So we first choose that the dj is greater than di, and then we choose dk dash be the largest of di. So this means, because it is dk dash we have selected as the largest, so this means k by 2 is less than or equal to dk dash, because we have created that much unique number of pairs. So but tau n is equal to k, and dk dash is less than or equal to root n. So this is how we have initially selected our pair. So this means tau n by 2 is less than or equal to root n, or we may say tau n is less than or equal to 2 times root of n. And similarly we can show our results. We can show our result for k odd. Now earlier I have considered k to be even. Now in the similar process you consider k to be odd, and in that case when k is odd we consider k minus 1 by 2 pairs, and repeat the process. Now in problem number 7 we want to show that tau n is an odd integer if and only if n is a perfect square. Now this is extremely simple result. What I want to show is tau n is an odd integer. What is the definition of tau n? Let's write this, and then we want to show if and only if n is a perfect square. So for tau n, let me to first also take what is a prime factorization of this n. So from here, let tau n is odd. So if tau n is odd, this implies tau n by definition is k1 plus 1 up till kr plus 1. This quantity is odd. This quantity odd means that each of ki plus 1 must be odd. Because if any one of this quantity is even or 2, the product will going to become the even. So we must need to take that each quantity is odd. If each of this is odd, this means each of ki plus 1 is equal to some 2 times some quantity j. This implies each of ki is nothing but 2j plus 1, this quantity. So this means the ki is even. So ki plus 1, sorry, what I've done, ki plus 1, this whole quantity is odd, so this means ki is even. So if ki is even, so this means what is n? N is nothing but p1. Now replace ki with this 2j, so this quantity would be 2j1 and so on pr, and this would be some 2jr. So this means it is p1 up till pr, and then you got the powers j1 j2 up till whole square. So you got a perfect square. So this is a little obvious. And conversely, if n is a perfect square, what we need to show is, if n is a perfect square, I need to show tau n is an odd integer. So suppose if n is a perfect square, it is a square, and in the prime factorization form, it is something like p2 to be kr, and I want to show that this whole quantity is a perfect square. So this whole has to be a square. So this means it is p1 to the power 2k1 up till so on p2 to the power 2kr. And if I want to find its tau n, this is nothing but 2k1 plus 1 and so on the power 2kr plus 1, and which means each quantity, this is odd. So this is odd. So the product of odd quantity is finally odd. So that shows that the tau n is odd integer. So this proves the first part. Now let's prove the second part, where we want to show that the sigma n is an odd integer if and only if it's a perfect square or twice a perfect square. So for the B part, let's first suppose that sigma n is odd. If sigma n is odd, again let me to take first the value for n. This is some prime factorization, and we know by definition of sigma n, we have here, this is nothing but it is p1 to the power k1 plus 1 minus 1 upon p1 minus 1 and so on pr to the power kr plus 1 minus 1 upon pr minus 1. And if we just cancel out this term, this will become actually a sequence. This will become a sequence of this type, k1 and so on 1 plus pr plus so on plus pr kr. Now for sigma n to be odd, we want each of these terms has to be odd, because the product of odd quantities are odd. So this means, now when we say that each quantity is odd, so there are and there is no restriction currently on pi. So if any of the pi is this quantity 2, then pi raised to power n, because 2 raised to power any quantity is also further even, and this implies 1 plus 2 square plus so on plus 2 to the power some n. This is odd. So there is no problem if pi is even. Now if pi is odd, in that case again we have this quantity that pi raised to power n, this quantity is odd. And if this quantity here, if the power ki is odd, now we are considering on the power also, then we have pi plus pi square plus so on plus pi to the power ki. This quantity is odd, but adding it to 1 will make it even. So pi to the power ki, this quantity is now even. So this means ki must be even for this whole quantity to become odd. So this whole quantity to become odd. So if ki is even, so that means we have pi to the power ki, that is equal to pi to the power some 2ji. If it is odd, this means it is p to the power ji whole square. And we say now here, if 2 is a factor of n, so what we can write simply, n is 2 to the power k into the remaining, because this is going to be the first prime, the remaining prime now I am writing here, p2 to the power prjr whole square. So this is nothing but it is 2k times some quantity a square. So this becomes that it is a square or twice of something. Now also further we see what is the condition on a. If k, what is the condition on k? If k is even, k is 2s. So this implies n is nothing but it is 2 to the power 2s, and then we have a square. This means it is nothing but it is 2s a and whole square. So it becomes again the perfect square. So it becomes again the perfect square. And if k is odd, so suppose that k is some 2s plus 1. This implies n is nothing but it is 2 to the power 2s plus 1 a square. In that case it is 2 times 2s a whole square. So it is twice the perfect square, 2 times the perfect square. So that is what we have to prove as the result. Now the converse hold. Now if we proceed in the back step, converse will hold immediately. Converse hold if we follow back. So I'll leave this for the, if we follow back. So I'll leave this as an exercise. I'm sure we can do that as an exercise.